Hello and welcome to Controllerstech. In this video, we'll learn how to interface the MFRC522 RFID module with an STM32 microcontroller. The MFRC522 is one of the most widely used RFID, radio frequency identification, modules for contactless data communication. It operates at 13.56 MHz and supports RFID cards, tags, and key fobs that follow the ISO 14443A standard, such as the popular MFRC Classic cards. This makes it a perfect choice for applications like access control, attendance systems, and smart identification projects. The module can communicate with microcontrollers through SPI, I2C, or UART interfaces, but SPI is the most commonly used because of its higher speed and simpler implementation. Being compact, low-cost, and efficient, it's a great way to add RFID functionality to embedded systems like the STM32. With just a few proper connections and the right library, you can easily read and write data to RFID cards. It's an excellent tool for learning about wireless communication and secure authentication techniques. For this demonstration, I'll be using the STM32 F103C8 microcontroller to interface with the MFRC522 module. We'll begin by reading the unique IDs of the RFID cards that come with the module. After that, we'll configure the system to perform specific actions whenever a valid card is detected. Let's start by opening the STM32 CubeIDE and creating a new project. As mentioned earlier, I'm using the STM32 F103C8 board. So, select that, give your project a suitable name, and click Finish to create it. The first step in our configuration will be the clock setup. We'll use an external high-speed crystal to provide the clock signal. The blue pill board includes an 8 MHz crystal, and we'll configure the system to run at its maximum 72 MHz frequency. Next, go to SysDebug and enable Serial Wire Debug, SWD, to allow program debugging and flashing. Since we're using SPI to communicate with the MFRC522, let's enable SPI1. The pins PA5, PA6, and PA7 will be used as SCK, MISO, and MOSI, respectively. We'll also need two additional pins, one for chip select and another for reset. So, configure PA4 and PA3 as output pins and rename them according to their functions for clarity. Now, let's configure the SPI parameters. Make sure the data width is set to 8 bits, with MSB first. Choose a prescaler that gives a baud rate of around 1 megabit per second. The SPI mode should be mode 0. So set the clock polarity to low and phase to 1 edge. We'll also enable USART1 so we can print debug logs to the serial console. For this, we only need the TX pin, PA9, to send data to the terminal. In addition, I'll connect two LEDs to indicate the card status, one LED for each card. Configure those pins as output as well. Finally, let's take a look at the connection diagram to understand how everything is wired together. Here you can see the connections between the RFID module, FT232 USB to serial converter, and the STM32 F103C8. Make sure the RFID module is powered using the 3.3 volt supply from the development board itself. The module is not 5 volt tolerant, so applying 5 volt to it could damage the chip. Ensure that all signal lines and power connections stay within 3.3 volt levels. Let's review the pin connections in detail. The reset pin from the module is connected to PA3. The MISO pin is connected to PA6. MOSI is connected to PA7. The clock pin is connected to the SPI clock pin, PA5. And the SDA or CS pin is connected to PA4. For serial communication, the UART1TX pin, PA9, of the STM32 is connected to the RX pin of the FT232 module. This setup will allow us to send log messages and debugging information directly to the serial console on your computer. We've also connected two LEDs to indicate the RFID card status, one connected to PA8 and the other to PB15. Since STM32 pins output 3.3 volt logic, always place a 220 ohm resistor in series with each LED to limit the current and prevent the LEDs from burning out. That's all the configuration we need to do inside CubeMX. Once everything is set up, click Save to generate the project code. I've already prepared the library files required for this project. You'll just need to copy them into the project folders. These files are available for download. You can find the link in the description of this video. There's no need to modify anything inside the MFRC522 source file, as it already handles the core functionality. However, in the header file, you can choose which type of logs you'd like to display. For this demonstration, I'll keep the user logs enabled. But if you face any issues while testing, you can also enable the debug logs for more detailed output. Alright, now that everything is ready, let's see how to use this library to interface the RFID module with STM32. Include the MFRC522 header file inside your main.c file. The first step is to configure the MFRC522 structure according to our hardware setup. This structure includes a few important elements: the SPI instance, chip select port and pin, and the reset port and pin. Let's configure these parameters based on the connections we made earlier. Since we're using SPI1, and we've already named our GPIO pins according to their functions in CubeMX, assigning them here becomes straightforward and easy to understand. Next, we need to create a custom write function. This function redirects the output from the printf command to the UART interface, so that any log or debug message will appear on the serial console. In this setup, we've configured UART1 specifically for logging purposes, so we'll route all printf data to UART1. Now, let's define an array of 4 bytes to store the card ID that we'll read from the RFID tags. Inside the main function, call MFRC522 init to initialize the module and pass the configured RFID structure as its argument. This will set up all the internal registers and prepare the MFRC522 for communication. We'll continuously read the cards inside the while loop. To start with, check if a card is detected using the waitCardDetect function. This function keeps waiting until a card is placed on the module, and once a card is detected, it returns status OK. After detection, call MFRC522 read UID to read the unique ID of the card and store it in the array we defined earlier. Then, log this card ID to the serial console in hexadecimal format for easier identification. Once the card is read, we'll wait for it to be removed using the waitCardRemoval function. This function also waits indefinitely until the card is taken away from the reader. With this setup, we should now be able to read and display the unique IDs of any RFID cards placed on the module. These IDs can later be used to trigger specific actions or control devices based on which card is scanned. Both of the functions we used for detecting and removing the card wait inside a while loop. If you want to perform other operations alongside RFID reading, you can replace these while loops with for loops or non-blocking checks, allowing other parts of your code to execute simultaneously. Now, let's build the project and flash it to the STM32 board. Once the code is uploaded, open the serial console to monitor the logs. You'll notice that the MFRC522 module initializes successfully. The log shows the RFID version as 0x12, which usually indicates a non-original or clone module, but still functions perfectly for reading card IDs. For reference, the original modules typically report version 0x91 or 0x92. After initialization, the code waits for a card to be placed on the reader. Let's test it using the card that came with the module. Once the card is placed, it's detected successfully, and its unique ID appears on the console. The system then waits until the card is removed before proceeding further. Make sure to note down the card ID, as we'll use it later in the code. Now, let's try scanning the keyring tag that also comes with a module. As you can see, the ID for this tag is also displayed on the console. So, we now have the unique IDs for both the card and the keyring tag. In the next step, we'll modify our code to perform different actions depending on which card or tag is detected. In this part, we'll compare the card IDs we just noted with the predefined IDs in our program. If the ID of the first card matches, we'll turn on the first LED for 1 second and then turn it off. Similarly, if the second card's ID matches, we'll turn on the second LED for 1 second and then turn it off as well. All right, let's build the project again and flash it to the board. Now, place each card on the RFID module one at a time. You should see the LED turn on for 1 second whenever a recognized card is placed on a reader. When you place the other card, the second LED should light up in the same way for a second. As you can see, both cards are being detected correctly, and the LEDs respond exactly as expected based on which card is scanned. Instead of LEDs, you can also use a buzzer or any other output device to indicate card detection. This can make the system more interactive and useful in real-world applications. If you want to expand this project, you can implement freer tools to manage multiple tasks simultaneously. For example, reading RFID cards, controlling outputs, or communicating with other peripherals at the same time. One important note: if your system clock is set higher than 72 MHz and you experience issues with card detection, try increasing the delay inside the read and write register functions of the library. This small adjustment often stabilizes communication between the STM32 and the MFRC522 module at higher clock speeds. With that, we've successfully interfaced the MFRC522 RFID module with the STM32 microcontroller using the SPI interface. This setup can serve as a foundation for advanced projects, such as access control systems, attendance tracking, or secure identification solutions. That's it for this tutorial. You can find all the project files and example code in the link provided in the video description. If you have any questions or doubts, feel free to leave a comment below. Thank you for watching. Keep learning, keep experimenting, and have a great day ahead.